the rule. The bigger rule one is the rule locus start at the pole and end at the zeros of the open loop system. So say here we consider K, QS, PS equal to 0. So here this open loop system, that means the QS, PS, okay. So from here, let us rewrite this equation become like this, okay. So, so from here you can see when K equal to 0, and that means the characteristic equations becomes PS equal to 0. Okay. So when K equal to 0, that means that is the starting of the root locus. So the root locus starting at the roots of PS equal to 0. So the roots of this, that means so the root of the PS means the poles of our system. And also we see when K equal to infinity, so that means these characteristic equations can be approximated because K is so large, so we can ignore the PS, so that meaning leaving the characteristic equation become like this. Okay. Again, because K is large, we can ignore these portions. So when K equal to this one, that means the QS, when K equal to infinity, then basically this one equivalent to is this one, okay? So when K equal to infinity, that means the ending of the root locus. Okay, so ending of the root locus is at the root of the QS, so which means whose root. And we know by definition we call these zeros. Okay, so basically here for this statement we explain why we start with poles and end up at zeros. And again, the poles and zeros are we call the open loop system. That means it's only for this one. Okay, and this is the characteristic equations of the whole entire closed loop system. Okay. The second rule is once we identify the location starting and ending point, then the second one is asymptotes. The asymptotes basically is this. The first one, the orientations, O-R-I-E-N-T-A. The orientations of the asymptotes are given by this equation. Let me use theta. And theta is equal to 2L plus 1 divided by n minus m times 180 degrees. And here the L equal to 1, 0, 1, 2, etc. until this number will become cycled when we will see it. Okay. So basically here, because this is a parameter of the L, so here we simply put it to here, indicating there's a couple orientations. Okay, there's a number of the asymptotes. Okay, depends on the proof of the system. But if you keep applying the number of the L from 0 to, then you will find the result will become cyclic. Then you can determine the sense. Okay. Again, this is a result, and the reason why is we can from the big approximations. Let me give the result first, and then I provide the explanations again. Okay. And the intersections, of the asymptotes is at real numbers at sigma 0. So the asymptotes always intercept on the real axis. Okay. And now we simply figure out what is the location on the real axis, and sigma location of the asymptotes, intersection of asymptotes, is given by this formula. That is the summations of the poles minus the summations of all the zeros. So this meaning the summation of all the poles, that means the summation of the zeros. We simply added up them together. If there are complex conjugate poles or zeros, you simply add it up, then the imaginary part will cancel from each other. Okay, so basically this result will give us the real numbers. Okay, we simply do this one. And the explanations is this. So again, we can consider one characteristic equations, and that can be the simplest format will be like this. But now to explain this, I want to have a better and detailed description for P and Q. So here I consider is K. And so, for example, the Q can be factorized into, say, S minus Z1. That is the root, and multiply S minus Zm. And for the poles here is S minus P1. Can allow me to follow up with my lecture notes. Here I use sign, okay? So that means here is equal to 0. So that means the open loop zeros are at minus Z1 and minus Z2 and etc. minus Zm. And the open loop poles are at minus P1 and etc. and minus Pn. Okay, so for this case here, we're assuming that n is greater than or equal to m for the practical systems. Okay, so basically, the number of the zeros always less than or equal to the number of the poles. Okay, so that's the situations we come up with. So we consider this one, then orientations. Again, here the explanation is to repeat what we exercise in the intuitive examples there. So for asymptotes, basically asymptotes is an approximations and approximations to the given to the roots of the given characteristic equations. Okay, so asymptotes is an approximation of the given characteristic equation, the roots of the given characteristic equation. So which means the asymptote is a root. The asymptotes basically are the collection of the roots of certain approximated characteristic equations. So here we can say, consider under these things, we consider still right now we under this topic, we consider and approximated characteristic equations. Okay, so based upon this, we try to find the roots of this one, and hopefully using that one, we can find in the asymptotes information. Okay, so for this one, compared to this one, basically here we can try is, again, from our intuitive exercise, we can try to do the roughest approximation of this. And so by looking at this one, the degree of the denominator polynomial is a degree of n, and this is a degree of m. Okay, so here we do the very approximate, very rough approximation. So basically, this approximated characteristic equation we can consider is like as m. By doing so, we simply ignore the lower order terms. We simply, for numerator, for denominator, we simply pick up the highest term. Again, we do the approximation, we can do however we like. Right? So here, that is a one option here. Okay. So for this case, basically that equivalent is k and s. No, that we can simplify this one as m minus m equal to 0. Okay. So from this case, we have by the phase. From the phase criterion, that means okay, let me do one more time. So basically for this one, let me rewrite here. So basically 1 as m minus m equal to minus 1 over k. Okay, and again, if I would, didn't provide any specific information, basically in these chapters, okay, in these chapters we're working on the domain is k, non-positive, non-negative. Okay, if I would forget to write that one, you have to assume that's a range. So here k is non-negative, so basically this number will be always negative. So here we look at the phase. The phase of this system basically is the left-hand side is the phase angle of the numerator, which is 0, minus the phase angle of the denominators, which is minus as m minus m. Okay, and the phase on the right-hand side, because this is a negative number, so the phase is on the right-hand side is minus 180. And also we have the multiple numbers, so we can say L times 360. Okay. And for 360, maybe we can rewrite is 2L plus multiply 180, so they are equivalent. Okay, I try to match the equation there. Okay, so here, again, from our previous example, we always is L multiplied with 360, right? So here I simply rewrite this one. Okay, with this one in mind, and again, we can simplify the right-hand side is m minus n. The left-hand side is this one. This is angle here, and equal to minus 180 plus 2L times 180. So what is this? This one representing is the orientations of the S for the approximated characteristic equations. And right now for this approximated characteristic equation, that is to approximate as the asymptotes. So which means this representing is the angle or the phase angle of the asymptotes. Okay, we're starting from here kind of literally. So basically this one representing is the phase angle of asymptotes. Okay, so that is the phase angle of the asymptotes. Okay, so therefore here that one in terms of our definition, that one using our symbol here, that's theta L. So basically theta L equal to this one, then we simply rewrite this equation. So theta L equal to this number divided by n minus n. So basically that is this number we write here. Hundred eighty. Does anyone see any discrepancies? Okay, let me do this a little bit more here.
Seems
okay,
like there's a sign difference.
Yeah. So from here, we do this one, do the calculation. The both side is minus 180 degrees, and the right hand side is minus 1 plus 2L, right? And then divide by n minus n. Doesn't matter. Okay, so from this result, we got is this one, and this is our explanations. However, the formula I give you is this one, so the difference is on the numbering of the L, right? Okay, but again, for here, for taking this one as a positive, maybe for this explanation, you know from, that is from where? From here. If you remember all the complex numbers, they are multiple values here. They basically the cycle. Okay, this is a complex plane. So let me make one example here. So here, if we consider a complex number, so the complex number, for example, the magnitude is theta, is sigma, and this angle is this one. So this can be expressed by this, right? For these particular numbers, if the theta is given to theta plus 360 degrees, this one also can be equal to j theta plus 2 pi, 360 degrees, or 4 pi, 6 pi, or minus 2 pi, minus 4 pi, etc. Okay, so basically that is the multiple numbers. So that means really here we not only confined to, I would say the L here, the L here can be any integer numbers. So if you have this concept here, basically it really doesn't matter here. This equation provided by, I believe, is by our textbooks. I follow up that one. So basically here the point is if you keep changing the L, I would say the L here can be any integers. If you keep doing the things, after the few try you will come to another cycle of the numbers here. Okay? So that's the explanation for orientations. And now I'm going to explain the approximation for the intersection here. So again, the explanation for the intersection, again, we do the asymptotes and do the approximation. And now to get the intersection of the asymptotes, I want to change my approximations into by this. Okay, so here I want to compare to this one. I want to compare with our strategy. So here let me utilize the approach. So rather than using the simplest approximations, and here let me leave it and let me figure out what is the good one I want to try. And compared to the previous approximation, we simply drop off all the lower order terms. And we keep the highest terms for the numerator and denominators. And now for this case, I want to keep the first two terms. For example, this is the first two terms. That is, I want to keep is Sn plus and Z1 plus Z2 plus Zn and Sm minus 1 plus something. I want to keep the first two terms and by ignoring the lowest order term here. Okay, the same thing from this, the denominators, if we expand it, that is the highest order term is P1 plus Pn and Sm minus 1 plus, then we keep the first two terms there. Okay? So this is our approximations. And on the other side, if we want to find an intersections at a point, and again, we look back to our complex number here. if we wish there's an intersection, intersection of the straight line, that means something like this. Okay, they have to, here we're showing is the three straight lines. If the three straight lines must meet at the same point on the complex plane, then their format must be in terms of this kind of things, and say S minus sigma and certain power, and let me say a certain power, say m power, and something like this one. Okay, only have this form, we will guarantee these intersections, the common intersections there. So to have the common point of the intersections, here we assume the power will be, say, sigma, okay? And what is the power of this? And that one is determined by this. The difference between the numerator and denominator is n minus n. So here we put the n minus n here. So that is the one we determine, that is the form. And we have this form because here we require for the asymptotes, doesn't matter how many number of the straight lines for the asymptotes, they intersect with each other at one common point. So that is the reason we set up this form. Okay, so with this form determined, then the remaining is compared to with this one, then we want to determine sigma. So that is the remaining calculations. Okay, so here is approximated, and this is simple, so let me erase this one here. I want to utilize the space. So here I want to make a tables and to compare. So approximated characteristic equations from the given, and so that means, let me copy here, 1 plus k and Sm plus Z1 Zm as m minus 1. Okay, so basically here I have ignored the higher order terms here. I simply pick up the first two terms. The same thing, here I pick up the first two terms. Okay, so that is approximated. Those information are from the given format. And here, compared to the form we like for describing the asymptotes is this one. Okay, and our job right now is to determine what is the sigma by comparing the two forms. So that means right now we're asking is making the two terms equal, right? So that is our second, the little bit finer approximation. And so right now for finding sigma, we simply compare the two functions and then we find the relation there. Okay, so how to do it? We can try to simplify this one, and simplify this one, hopefully can get into that format there. And so, for example, here you can try is you simply divide the numerator by the denominators, and or whatever the algebra techniques you can try. Basically, that one, let me do this one step by step. So basically here, let me do this, n plus sigma zi and Sm minus 1, and this is m sigma pi as m minus 1. Okay. And right now I want to have the numerator become 1, so that means both the numerator and denominator are divided by the numerator, right? So in this way, how to get this one? And that should be easy. So we simply do the part calculation n plus sigma pi as n minus 1 divided by numerators as n plus zi as n minus 1, right? We simply do these calculations. So for this one, this is as n minus n. Okay, so that is as n plus zi and as n minus 1. Good. Okay. So this one will be equal to sigma pi minus sigma zi and times as n minus 1 here. So we keep doing, so that one, to get this one disappears, then we multiply is pi minus zi and multiply with as n minus 1. So basically here, this one multiplied with that one is sigma pi minus sigma zi and as n minus 1 plus something there, that lower order term I don't care because that is asymptotes. So from here we can approximate it's equal to 0. So therefore that number can plug into here plus sigma pi minus sigma zi and as n minus 1. Okay? So we can do this. So here again, there's a hand calculations. And now for this case, for this side, we can expand it. So here we do the expansions. So for this case, we expand it. That'll be as how to do this expansion. For this one, if you know a plus b n, so any numbers, let me say, okay, how about use that? N, how about this one? Okay, so for this one, once we expand it, basically that is a n times and this one, a n minus 1b plus n2 a n minus 2b squared. Basically, this one is the notation equal to n factorial and minus 1 factorial times 1 factorial. So n2 is n factorial and minus 2 factorial and 2 factorial, etc., etc. Okay, so basically here this one is an plus n minus 1 and plus something. Okay, using this equation, basically here we can simplify this one. If you want to expand it, you can do it. So basically that is minus sigma times n minus n and times sigma n minus 1 and plus the lower order term. So let me ignore the lower order term here. Okay.
Does there need to be a K in front?
Huh?
Does there need to be a K in front?
Yes, thank you. Yeah, the K is here. Sorry. Okay. So again here we have ignored the lower order terms. So we approximate here. Again we ignore the lower order terms here. Okay. So right now again in both sides we simply compare the first two terms. Actually, the first term are equal, then we'll compare the second term. So comparing the second term, you can see this number, coefficients of the second highest degree term must be equal to these coefficients. So from there, you can see sigma will be equal to minus n and sigma pi minus sigma zi. Okay, so, oops. Good. we are still good. So from here you can see compared to the coefficients, that's the coefficient, then we have this one, right? Good. So keep that in mind, and here I write up is in terms of the whole and zero. So for our case, if you remember, for this one, can you see, compared to this one with that formula, it seems that there's a sign difference. No, but I don't want to confuse you. Either this one or that one. Okay. And if you remember, for our problems, recall our open loop zeros are minus z1 and minus zm, and our open loop holes are minus p1 and etc. minus pn. Okay, so basically here, applying the formula, either you want to apply in terms of the symbols here, or you simply want to apply in terms of the literal description here. You got my point? Okay, if you didn't get it, that's okay. Either one, okay. So with this one, then we can try one example here. Let me get a space. So here, example here, we want to plot the root locus for this characteristic equation S and S plus 4 squared and plus 4 squared. Okay, for this problem, I already be kind to you. I factorize, and for the second term, I already put into the form. We can easily find the real and imaginary number, the part of that root. Okay, or otherwise I have to convert. So for this case, in the open loop, 0. For this case, it's nothing, not available because there. So basically, here we can see all the zeros are located at infinity, and open loop holes for this case is 0, and then minus 4 plus j4 for this case. Okay, so easily we can plot. When you plot by hand, and here is a good exercise, try to plot it to scale at your best. Okay, otherwise later on you're going to screw up by helping yourself observing the orientations. So here 1, 2, 3, 4, and 1, 2, 3, 4. Okay, and for this case we have holes here, and 1, 2, 3, 4 will be here and here. Okay, so here I put the scales, and so if you like, you can keep writing these things, and that is s equal to 0 by k. So this is s equal to minus 4 plus j4. Corresponding is k equal to 0, and s equal to minus 4 minus j4, and corresponding to k equal to 0. Okay. So the 3 spots are the starting points of the root loci. How many branches of the root loci we're going to expect for this problem? 3. Why? Because you always look for the degrees of the denominators, which is the degree 3, so 3 branches. Okay, now we plug into here the second rule. For the second rule, for our exercise here, we can, for this case, the theta L will be equal to n equal to 3, and m here is 0 for this example. and 2L plus 1 times 180 degrees. So here basically is 3 2L multiplied 180 degrees. So we keep cycle the numbers here for L. So when L equal to 0, that is 60 degrees. When L equal to 1, so that is 120 degrees. Is that right? Yes. And then when L equal to 2, basically is 3, 4. Is that right? Sorry. When L equal to 2, so that is, sorry. Let me restart. Let me start over. So when L equal to 0, and this number equal to 180 degrees. And when L equal to 1, so that one equal to how much? 120. When L equal to 2, and that is 240 degrees. Right? How come I didn't get it?
I think you're missing the plus
Missing
1.
plus 1. So I know I kind of stupid here. So this will be when L equal to 0 plus 1, so that's 60 degrees. When L equal to, yeah, you see, I am mistake here. 3, 2L plus 1. Yeah, that is the right one. So that is 180 degrees. And then for this one, that is 300 degrees. Okay? And then if you want to continue when L equal to 3, then that will come up with is 3 times 180, so that is 420 degrees. 420 degrees basically in the cycle that it is equal to 60 degrees. Okay, so that's the reason why I said once you try, then you will see the cycle. Basically, the three numbers are within it. So here the orientation has 60, 180, and 300 degrees. And now the intersections for this example here is 1, 3 minus 0, and the summations of the poles. The summation of the poles is 0 minus plus minus 4 plus J4 plus minus 4 minus J4, right? So that's summation of the pole. And minus the summation of the 0, and here we don't have a 0, so that is 0 there. Okay, so for this case, that will be 3 minus 8. Okay, good. So the intersection will be here. Minus a over 3, so about here. So that is our intersections of the asymptotes. The asymptotes is in 60 degrees, 180 degrees. So 60 degrees and 180 degrees. And then 360 degrees. 360 basically is minus 60. Okay, and I don't know, my drawing will be correct, but something like this. Okay, so I use dash line to indicate. Okay, so we continue. Scott probably can